Okay, so select the asymmetric atoms in serine. So you'd get serine, and you'd draw it out, or you'd have it drawn. And then you need to select the ones that are asymmetric. So what are ones that are asymmetric? They will not be symmetric. Hey, was there a thing that I said about chirality? Yeah, if it's symmetric, it is achiral, isn't it? So that means if it is asymmetric, well, chiral ones have to be asymmetric, right? They cannot be symmetric. Chiral and symmetry are opposites.
Oh,
okay. If you're symmetric, you could never be chiral. Period. Yep. Symmetry means that, literally means that you have a mirror image that can be superimposed. That's actually the definition of symmetry. So, by definition, chiral and symmetry have to be opposed to each other. Okay? Now, you can actually have, to a degree, like symmetry goes beyond just carbons and atoms, right? So there's actually more to symmetry than just that. But yeah, by definition, they have to be opposed. And so what are you looking for then? Well, you're looking for a carbon or an atom that would be chiral, right? That would be a big, big tip and automatically mean it is asymmetric, not symmetric, right? Okay, we look at serine, and, well, these things don't have enough groups to be asymmetric, do they? How about that one? Is that one symmetric or asymmetric? Do you want to try chiral first? Yeah. Okay. Is that one chiral or achiral? There's two of you. One of the answers each you get right. Sure.
Let's see, I'm trying to think about it because I remember us talking about like it's a double bond. And you act like there's two there. So
that has nothing to do with this.
What was that?
No. That is the R and S. That's the priority of the groups attached.
Oh.
Yeah.
Yeah, that's right.
Yeah. So this, if you don't have enough complexity, then automatically it's going to be symmetric, right? How about a sphere? Is there any way you can turn a sphere that it's not the same? No. You start putting a dot on it, one dot. Well, now when you turn it, it changes things, right? But it's still symmetric, I mean, and it's still not chiral, is it? It's still achiral. You put two dots on it, and things start changing more, right? But again, it's still symmetric, isn't it? Because you can divide those dots in half by drawing a line through them, right? Okay. So then you start putting three things in. Well, that still has plane of symmetry, doesn't it? Dissect to the distance between two of the dots, right? What if you start doing four dots? Each of them are different. If each of them are different.
Oh, each of them are different.
Yeah. Think of it like your hand, right? If you only have 3 fingers, then you wouldn't have enough complexity. Well, only 2 fingers because you have your wrist. That's 1 point already. You wouldn't have enough complexity to actually change things. You wouldn't have a right and left hand. You'd have 2 pinchers, right? Like a robot. You seen a robot? 2 pinchers, right? Or a crab? 2 pinchers? Doesn't matter whether they're up or down or what, right? They're symmetric. It's not chiral, is it? They don't have a right and left. Which one's the left hand for a lobster?
The big.
Doesn't matter, does it?
Only have two things.
Yep, they're pinchers.
Big arm cramp.
Huh? So when you have 3 points, you can't be chiral, can you? You're always symmetric. And so this has 3 things off it. It's achiral. It has symmetry, doesn't it? Yeah. Remember, they're opposite things. Chiral, symmetry are opposites. So what happens when you have 4 different things? That would be like your hands, isn't it? You have 3 fingers on that hand now?
But on this one, you have.
This right here, this carbon has a hydrogen that's not being shown, right? Because all carbons have 4 bonds to them unless they have a positive or negative charge, right? And so you have your hydrogen, that's 1. You have your nitrogen, that would be 2. You have your group with the oxygen off it here, that'd be 3. And you have this group right here, right? It'd be 4 different things. And so that has to be chiral, doesn't it? If chiral and symmetry are opposites, that has to be the opposite of symmetry, which means asymmetric, right? And so that would be an asymmetric carbon. Another way of thinking about that is, could you draw a plane of symmetry through this?
No.
No, you could not.
Yay.
Because there's no 2 groups you could fold into each other, right? That's what you need for a plane of symmetry, isn't it? This one has a plane of symmetry in the plane, isn't it? In the plane of the paper, or the screen, going through these oxygens and that carbon. Literally, you're seeing the plane of symmetry. Right? Okay. Same thing with all these other groups, right? Can you see that? There's plane of symmetries on all these. Because they always have duplicate groups. This has 2 hydrogens. This right here has 2 lone pairs. It depends on how you're defining symmetry. But in this case, due to the fact that it has 2 positions of its possible bonding positions or tetrahedral arrangement, that would be, remember the electronic arrangement would be tetrahedral, and those are lone pairs that are taking up those positions. No, it cannot. Because it has 2 lone pairs. Yeah, it forces it into a configuration that it has to be chiral. Yeah. It has a plane of symmetry. If you made this like, I'll give you kind of a weird example. Let's look at this one. I'll give you a weird example, okay? Because the example will make a little more sense. Okay, this has 2 hydrogens on it, right? And remember, this would be that, looks like a pyramid, right? Okay. Because one of the tetrahedral positions is taken up by a lone pair, right?
Yes.
Okay. So right now it has 2 hydrogens, so it has a plane of symmetry going between those 2 hydrogens. Okay? Can you see that in your head? Okay. But if you had, instead of a hydrogen, a CH3, would that have a plane of symmetry anymore? No, it wouldn't, would it? Yeah, because one side would have a hydrogen on it, right? Or one side would have a CH3 on it. You couldn't line it up so you can reflect across no matter what you do to it, right? Any which way you go, you never get a plane of symmetry. Because that lone pair would be one of the positions that would be that 4th position, right? Meaning that lone pair makes that position empty. It forces it into a configuration that it is not planar. Because the atoms can't be in that space, can they? Kind of like the lone pairs here force this into bend, don't they? Okay? Now, if you had a boron, it doesn't matter what you put on it, because it is trigonal planar, literally planar. It has a plane, doesn't it? It's all in one plane. So it doesn't matter what you put on it, it automatically is in a plane, isn't it? That means it has a mirror image that it can superimpose. That makes sense?
Is there another one like this?
Yeah, sure. No, symmetry, huh? Okay, so let's look at these symmetries. Select the asymmetric atoms in Ethros. Ooh, fancy. Okay. By the way, you would normally draw this in a Fisher projection to make this easy. That's why you do that. That's why we always draw Fisher projection shapers. Okay. So again, what are you looking for? Yeah, asymmetric atoms. What's the easiest way to do that all the time? Needs 4 things around it that are different, doesn't it? Yeah. And you can take a shortcut by including lone pairs in that. For carbons, you don't need that shortcut. You can just look at what's attached to it, period, right? Yeah, makes 4 bonds. You need 4 things different. There you go. That's nice, right? For other things that are not carbon, though, which means 90% of that cases, we're already covered by just having 4 things attached to it, right? You have 4 different things attached. Carbons are the majority of the cases. Cool. But 10% of the cases are going to be things like oxygens, nitrogens with like a nitrogen with a positive charge. Okay? So unusual cases, fringe cases. So you can go, do I have 4 different things around it? And that still works. Okay, so I look at these, and the first place I always want to look is the carbons. They're easy, right? How many things are attached to that carbon? If I have a double bond, automatically, there can only be 3 things attached, right? Because the double bond uses 2. If I have a triple bond, there can only ever be 2 things attached to a carbon, right? So that's an easy, quick, fix. I don't have to worry about it. So that has to be symmetric, doesn't it? And that actually is trigonal planar as well, by the way. Remember we talked about that? So if you understood the geometry of trigonal planar, I have 3 things attached to it. That means I automatically have to have a triangle in a plane, don't I? Planar literally means it's in a plane, right? So it's always symmetric. Has to be. If I have a triple bond on a carbon, it's linear, isn't it? That means I have an infinite number of planes to do it. It's even more symmetric. All right. I look here. Well, there's 1, 2, 3 different things I see, but carbons always have how many bonds? 4. So that means there's 4 different things, isn't there? And that means that is a asymmetric. It's chiral, exactly. And that's actually the ultimate goal of this exercise, is learning how to identify chirality and understanding chirality. Okay? Okay, so how about that one right there? So I have that. That looks different. That looks different, doesn't it? And so I have 3 things I see that are different, and then a hydrogen, so that's 4 different things, isn't it? And so that is, again, you got it. It's chiral like the other one. Yeah. Okay, and so the next one I go to, is that different?
See, I want to say no, because it would still have 2 bonds.
I have one, two things that I see. Two hydrogens, so automatically there's two hydrogens. Those can be exchanged without knowing the difference.
Oh, so since they're the same,
Yep.
that's what
That's another way of thinking about it. Remember we talked about in other videos, which you may see later if you look at these in order, because that's actually a later concept. If you look at enantiomers, when you want to make the other enantiomer, you simply exchange any two groups. And so that's a good test for chirality as well. Can you exchange two groups and get the same thing? Exactly. Because that's how you would make the mirror image, right?
So since this is two hydrogens, we can flip off those either way, so then it has to be a symmetric.
You got it. Yep. That's another way of looking at it. If you can exchange two things around there, it automatically means it's symmetric, doesn't it? Because that's another way of looking at symmetry. Okay. And notice that again, these oxygens are typically symmetric because they have lone pairs. Two lone pairs that force everything else in a plane of symmetry. Okay? And so typically oxygens will always be symmetric. Unless you get a positive charge, exactly. And then you have to think about it. Okay? Even 90% of cases where oxygens are positive, it's a hydrogen on there and they're still symmetric. Or they have a double bond and they're still symmetric, right? Okay. Is there any places that you don't understand why this would be symmetric?
It wasn't double bond on hydrogen.
Okay. Okay. All right. So, where do we? Let's just go through this. This one.
Oh, so it's got three, so that would be some achiral.
Yeah, achiral or symmetric. You got it. Yeah. Hydrogens are always symmetric because they only have one thing attached. Yeah. Here. Yeah, you got it. By the way, a little footnote to this. If this had been an OH here, this whole thing would have symmetry. Because it would literally be mirror images.
Oh.
Can you see it? And so then nothing would be chiral. Everything would be symmetric. So if you have overall symmetry, then that actually makes all the parts symmetric as well. Okay? So again, here, because we have that different group on here, that makes this entire thing have asymmetric groups. Okay? If this had been a mirror image, this did not have anything over here, you'd have a plane through the whole thing. Yep. It all would be achiral or symmetric. Okay. I wanted to point that out because you can save yourself a lot of time on a lot of test questions and stuff by just looking for planes of symmetry through the whole thing. There's a bunch of them that you can just go, oh, they're all symmetric. No chiral centers. Okay. So obviously that's one. You all had said that before, right? Okay. The next one, we look here. That's different, and then these have different sides, don't they? And so, yeah, chiral, or asymmetric, right? This one right here. You got it. And this is different because you have that OH there, right?
So okay. So if you, let's say, well, I guess that would end up being overall being symmetric. If we didn't have that group down there at the bottom, the H, the C.
Yeah, if you didn't have this here, the two CH3s on this carbon, you had another hydrogen here, well, then you would have had two hydrogens, and that would be achiral, right? Yeah. Got it. Okay. And again, then these would have not hydrogens you are not seeing, right? Yeah. And so they both have to be symmetric. Okay. Is that making sense for you so far?
They're symmetric. Oh, yeah. They're,
Yep. If you have two of the same group on them, automatically, yeah, achiral symmetric. Yeah. And you'd really want to get that down. Chiral, asymmetric, chiral, symmetric. They're opposites. Okay? By definition. Okay. Did you want to try something really weird with the nitrogens and stuff? Okay. Let's see if my tablet works. If it does, then that would be nice. So it actually is a very important skill. And this is something that I've always been particularly good at, and I leveraged as a skill that helped me in graduate school. So it's kind of an interesting side note to that. Okay. Uh-oh. Yeah, it's positive, right? So first off, what would that look like?
You would have one less lone pair. We would only have one electron. Right?
Oops, I forgot the last group. What do I want?
So, but does it have a plus?
It has a plus.
Oh, it has a plus.
Yeah. A nitrogen with only 3 things on it would be neutral. Because nitrogens typically have 3 things on them. So this doesn't have a lone pair anymore, does it? No. And so we have 3 different groups, don't we? The fluorine would be going backwards, chlorine would be going towards you, CH3 would be in the plane. Like so. Notice it does not have a plane of symmetry, and so that would be chiral, wouldn't it? How about like an oxygen? What if we had something like and again, that would have a positive charge to it. So we have 3 things around there that we're seeing, right? But I haven't put in something important, have I? I haven't put in the lone pair. There's only one, because the other one was used up to make a bond. Probably this fluorine, or maybe this hydrogen. Okay. And so that has, well, first off, it doesn't have a plane of symmetry, does it? No. If we tried to write in a plane of symmetry anywhere, it would have 2 different things on different sides. We don't have 2 things that we can replace each other with, right? If we try to replace the hydrogen and fluorine, swap those, no, that's not the same, is it? And so, yeah, that's asymmetric. Chiral. Got it. What if we have something like this? This can be a super common group that you see. Okay, you've already seen it a few times actually. So we've protonated the hydrogen, we've protonated that oxygen with one of these hydrogens, right? Typically very acidic conditions. And so what would this look like? Well, again, this would have the 2 hydrogens, right? And a CH3, again, a lone pair. I'm just drawing these out so you can see them. Okay. And I'm going to go ahead and give you some dash, 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 and your wedge.
And we have 2 groups. So it would end up being
It's symmetric, isn't it? Yeah. Because you have two groups you could swap with each other, don't you? The two hydrogens. Ooh, let's get a little complicated with this. I'm just going to write the bond here. This is CH3, obviously, okay? I'm going to do it lineage style. CH3. No, I get that a lot, so I'm going to... Uh-oh, what did I do? It's a deuterium, isn't it? That's the isotope of hydrogen. Is that the same thing as a hydrogen? No, it has a neutron, doesn't it? Oh my goodness. So you no longer have two things that you could swap, do you? This one's chiral. Uh-oh. That's called isotopic labeling. You do it to literally make things so they're no longer symmetric. And then you can tell two groups apart. Yeah.
Is this kind of, I know this is easy what we're talking about, but it was in the video, like the
Racemic mixtures are talking about enantiomers. And so a racemic mixture will be half-half. Typically it's half and half. Yep, it'll have both enantiomers. Well, they cannot be separated by typical physical properties. But if you use something that is enantiomer selective, you can. Okay? So for example, binding agents are one of the easiest ways. You can use a chiral binding agent, like a resin column, that has chiral groups that can bind to them. The chiral groups will fit one differently than the other, right? Kind of like if you try to put your right hand into a right-handed glove. It works, right? Put your left hand into the right-handed glove, don't work, right? So that's how you can separate racemic mixtures. You can separate them, but not by their base physical properties, typically. There are some fringe cases where the enantiomer, the different enantiomer, causes the two compounds to lay differently. Yeah, so it's a little bit more complicated than that, but yes, overall they'll have the same densities. They're going to have mostly the same boiling point, very little difference for most compounds. Mostly the same melting points, etc. Okay? Though do keep in mind, a racemic mixture oftentimes can actually have a boiling point elevation or a melting point depression. Because they can layer out differently. Yeah. It can cause them to essentially have two different species, right? Which would cause boiling point elevations. And, yeah. Yep. So it's kind of an interesting side note to